Hi, folks. Today on 1 Minute Math, you're getting the extended cut of graphing rational functions. So rational functions, this would be a pre-calc or maybe an Algebra 2 topic. We're talking about a ratio. The ratio part of the word rational means that I'm going to be looking at a function that is defined as a fraction. You can think of having a polynomial on the top and a polynomial on the bottom, and I'm dividing them. And the question is, what does the graph of this thing look like? How can I make sense of what the picture of this is going to look like and what that picture is telling me about this function just looking at the algebra? And it's scary for a lot of people. Graphing rational functions tend to be a really tricky subject for a lot of pre-calc folks, but I promise you it's not going to be that bad. There are a few key factors, no pun intended, we're going to be doing a lot of factoring, a few key factors that we're going to focus on to help make sense of what's happening, and you will be able to graph these, I promise. The three key things that you want to look at with the rational functions, the three things we need to figure out before we sketch the graph are: what is the end behavior of this function? Where are the zeros? And where are the vertical asymptotes? Okay, so end behavior is like, if I look at a rational function, typically these things have some vertical asymptotes happening. They've got a couple zeros. They've got all sorts of funky stuff going on in here. Okay, and we probably have either a horizontal asymptote or maybe sometimes it's like an oblique asymptote out here. Sometimes it goes all the way down to zero, the function it approaches, but a lot of times we've got a horizontal asymptote that is non-zero and two or more vertical asymptotes and a couple of zeros, and we get these pictures that look like this. They don't all look exactly like this, don't worry. Or don't get too excited, I should say. They're not all going to be carbon copies of this with just different numbers on. Those vertical asymptotes and those zeros and the horizontal asymptote, you can see how the placement of those items is going to drastically affect what our picture looks like, but those are the three elements we're looking for. All right, this would be the end behavior. What does the function do as x gets very, very large or very, very small? So it has a large magnitude, positive or negative. This is end behavior. And behavior. I hesitate to say horizontal asymptote because it is not always a horizontal asymptote. Although in this chapter, in this section, if this is what your class is focusing on, I'm going to guess that 90% of the rational functions you're going to be asked to sketch or graph will have a horizontal asymptote as their end behavior, because that's kind of the most, I guess, interesting or typical kind of these things that you have. These would be our vertical asymptotes, lines that the curve gets close to, and the zeros, the places where the graph either touches or crosses the x-axis. You might call these roots. You might call them x-intercepts. Okay, zeros is the word that I'm going to use. Now, looking at a rational function in its algebraic form, let's address those three things. The end behavior is going to be, I'm going to ignore everything but the highest power of x. So in this case, I got x over x. If I had another one just for funsies, let's say I had another rational function that had 5x to the fourth plus, I don't know what else, an x cubed, and then a 2x to the fourth minus 170 x's. Okay, I'll actually put something up here so we can see that really all that matters is the highest power of x. 17x cubed plus 368 x squared minus 10,000 x plus 37 and a half. Okay, so it doesn't matter how big or how ridiculous all the rest of that junk is on my polynomial parts, on my numerator or my denominator. What I focus on is the highest power of x. And why that is, if we're thinking about the end behavior, what's happening when x is very large and positive or very large and negative, if I take a very large number like 10 trillion and I take it to the fourth power, none of the rest of this stuff is going to even come close to how huge that is. 10 trillion cubed is very large, don't get me wrong. 17 times 10 trillion cubed is a very large number, but it's nowhere near as large as 10 trillion to the fourth. So for very large values of x, whether positive or negative, nothing but the highest power of x is going to influence the behavior of the output at all. So I'm just going to ignore it entirely. I pretend it's not even there. And looking at the highest power of x terms, I can simplify those. 5x to the fourth over 2x to the fourth, in this case, would be equal 5 halves, and that would be a horizontal asymptote of 5 halves. That's my end behavior. HA, horizontal asymptote. Our choices for end behavior, our word bank here is either going to be end behavior. It's going to be a horizontal asymptote, which could be at 0 or a non-zero number. And these are always y equals whatever that number is, whether it's 0 or something that's not 0. We could have an oblique asymptote, which will look like a y equals mx. You might say plus b. I just say y equals mx kind of thing. And an oblique asymptote means that in the end of my function, regardless of what crazy stuff it's doing here in the middle, it will approach a line. Okay. And the last thing is that I could have a non-linear end behavior. It could approach something like x squared or x cubed, where if I zoom way out, what we mean by end behavior is if I zoom way, way, way out, and I'm not caring about what's happening near the origin or near the y-axis, I will see a function whose end branches look like this other very simpler function, like y equals mx or y equals a number. Yeah. So end behavior would be horizontal asymptote or oblique asymptote. For these, I encourage my students to say goes to positive or negative infinity, choosing one. Like if I say, what's the end behavior on the right? In this case, they'd say it goes to positive infinity. Over here, they could say it goes to negative infinity because of the way those particular branches that I've drawn have gone. Okay, because we don't need to be terribly specific here. When we're graphing rational functions, it's not super important that we know exactly what function that they're approaching, not in this class or this conceptual area at least, but that we can determine whether or not those numbers will flatten out to be a single number or to approach a single number, or whether they'll go to positive or negative infinity. How we know if the horizontal asymptote is going to be at 0 or not at 0. So if I have, say, 3x squared plus 7x plus 2 over 8x to the 4th plus 5. When I look at the highest powers of x here, 3x squared over 8x to the 4th, if I simplify this, I get 3 over 8x squared. Think about what will happen to this number as x gets very, very large. You see how that fraction, as x gets really, really big and that denominator gets really, really big, that actually gets close to 0. So we can say if the denominators win, if the denominator wins here, it goes to 0. The horizontal asymptote will be at 0. If the numerator is bigger, so here I've got one where the numerator is larger. If the top wins, simplify this, I'm going to get 4x to the 4th over 5. We can see as if I plug in a bigger and bigger and bigger x value, that number will actually get bigger and bigger and bigger. This will go to positive infinity. If the numerator is bigger, that's when we get an oblique asymptote or a nonlinear asymptote, or I would say goes to positive infinity in this case. Where we get a horizontal asymptote is when the top and bottom, when the numerator and denominator have the same highest power of x. The end behavior equals horizontal asymptote at whatever number that those coefficients reduce to. So in this case, it would be 5/2. Let's go back to my original example here. Ignoring everything but the highest power of x over x is 1. The end behavior of this rational function is a horizontal asymptote of y equals 1. I'm going to go ahead and draw that on here. Because y equals 1. I'm not going to, this is what I'm not going to do. I'm not going to draw a nice straight horizontal line through solid line through y equals 1. I'm going to go out to the ends and I'm going to make a little dashed line. This is the end behavior. It is not the middle behavior. We're not saying that y equals 1 is a line we cannot cross. An asymptote is not a line that you cannot cross. That's a false definition if somebody told you that that's what an asymptote is. An asymptote is a line that a function gets close to. It may cross it. It can cross it infinitely many times if it wants to. It just has to get close to it. I'm not going to give you the technical definition of what an asymptote is, but it's very related to the idea of a limit. And it just means that the values are approaching. They're going to get close to that line. So as x goes to positive or negative infinity, my y values will get close to 1. And that's where I have that little dotted line drawn. All right. Zeros. You probably remember this from another course, but we're going to remind you anyway, that if I have 0 divided by a number, if the 0 is over the line, this equals 0. And if I have a number divided by 0, if the 0 is under the fraction line, then this is undefined, okay? Which in our case is most of the time going to go to positive or negative infinity. So if I have 0 on the top, In this case, that would happen when x equals 1. That is a 0 of my function. X equals 1 is going to go right here as a 0. If I have a 0 in the bottom, in the denominator of my fraction, in this case, that's when x equals -2, that's going to give me a vertical asymptote. Unlike horizontal asymptotes, vertical asymptotes will never be crossed. And that is because if I'm looking at a function, we're talking about rational functions, right? The function part of that name means that there's no x value that I can hit more than once in my function. I cannot go across this line because that would mean that I'm failing the vertical line test. So in this case, I can draw it straight through the axis because I know it's never going to be crossed. All right, now all we've got to do is put together our pieces. I have a line here that I must get close to. I'm always going to start on the right when I graph these things. The next thing that I see on my graph that I've marked is this 0 at 1, so I'm going to get close to it. There's nothing in this function to indicate that I'm going to bounce off of the x-axis here or do anything crazy like that, so I'm just going to go through. And now the next thing that I approach is this vertical asymptote, so I'm going to connect those dots. I'm actually going to make that look a little bit closer without touching. Now, what's going to happen here is that, like Pac-Man, if you've ever played the video game Pac-Man, when you leave the bottom, you come in the top. Or when you leave the top, you come in the bottom. That's basically what goes on in these rational functions. If I leave the bottom here, I'm going to come in the top. And the reason for that is that this is the number -2. Let's just plug in a number close to -2, like -1. -1 minus 1 or -1 plus 2, that gives me -2. That's a negative answer. If I plug in a number that's on the other side of -2, like -3, -3 minus 1 over -3 plus 2, that's -4 over -1. That's positive. So every time we cross through, like our x values pass over one of these interesting values of x, our horizontal, our zeros or our vertical asymptotes, unless there's anything in the algebra to indicate otherwise, which in this case there is not, we change sign. Which means if my y values were negative down here because I was exiting kind of the bottom of my screen, then as soon as I cross over that vertical asymptote, they're going to be positive. Next thing I approach is this horizontal asymptote, and I'm done. That is the picture of my rational function. Let's try another one. All right, here we go. I'm going to do a little factoring here of the top. Well, first I better do end behavior. 3x over x is 3. I'm going to have an end behavior of y equals 3. And one here. Y equals 3. If I factor here, 3 times x minus 2 over x plus 2, zeros of the top give me the zeros of my function. So x equals 2 is a 0. Zeros of the bottom, which would be x equals -2, give me vertical asymptotes. And I can see this one's actually going to look a lot like that last one we graphed. Starting from the right, just addressing what happens as I go from right to left. Sweet. All right, let's check this guy out. Negative x over x is -1. I've got a horizontal asymptote of y equals -1. Is that not? There we go. My top, negative x minus 2 equals 0, happens when x equals -2. So I've got a 0 at -2. The bottom, it's going to be 0 when x equals +3. That's my vertical asymptote. Remember, the denominator, zeros of the denominator give me vertical asymptotes. Zeros of the numerator give me zeros. And now when I connect the dots here, this is going to be funky. All right, so here I go. I can't go through here to get close to this asymptote because there's no 0 there. So I must go down. You can't just cross over the x-axis. That's like a rule number, whatever, rule number 3 or something if we're counting rules right now. If I go out the bottom, come in the top, next thing I notice is this 0, so I'm going to come over here. And I get close to my horizontal asymptote, and that's the graph of this one. Another strategy that you can employ if you are unsure of where things go, the more dots you have to connect, the easier it is going to be for you to put everything together. So if I find my vertical asymptote, or I'm sorry, my y intercept. If I plug in 0 for x and I get a y-intercept, that's one more dot on my graph that I can connect here. Awesome. Now let's think about this guy. I'm not going to multiply this all out, but if I did, I would notice that I'd have x squared plus or minus something over x squared minus something. And when I find the greatest powers of x and I divide them, I will get y equals 1. As a general rule of thumb, if you have exactly as many factors on the top as you have on the bottom, and there are no coefficients, you're going to have a horizontal asymptote of y equals 1. Zeros at the top give me my zeros. That would be x equals positive 2 and x equals negative 1. Zeros of the bottom give me my vertical asymptotes. So that would be x equals positive 1 and x equals positive 3. Let's connect these dots here. Starting at the right, got my horizontal asymptote, no 0, but the vertical asymptote is here. So I have to go up. I can't go down because I would cross the x-axis. Out the top, in the bottom. Next thing I see is that 0 crossing through. Out the top, in the bottom. Next thing I see is the 0. Next thing I approach is the horizontal asymptote. And there's my graph of that guy. Let's do one more of these before we address a couple weird anomalies. Actually, you know what? Let's go to one that we have to factor. Oftentimes, you're going to have to factor. If I factor out a negative out of the top here, I'm going to get negative x squared plus 4 minus 5 plus 4x minus 5. The bottom will be 2 times x squared plus x minus 6. This is going to give me negative x plus 5 x minus 1 over 2 times x plus 3 x minus 2. So sometimes you're going to have to do the factoring to get all of your different pieces. Don't be afraid of the factoring. Go look for my other video about factoring if that's scary to you. End behavior simplifies to negative 1/2. So I've got y equals negative 1/2 as my end behavior. Just for funsies, I'm going to find my, oops, I need the negative in there. My y-intercept is going to be negative 5/12. If I plugged in 0 for all the x's, negative 5/12. That is slightly greater than negative 1/2. So there's my y-intercept. That's an interesting point to know. Zeros of the top would be negative 5 and positive 1. Those are my zeros. Zeros of the bottom are negative 3. These are my vertical asymptotes. And positive 2. And here we go. Running out of colors. I'll use orange. Starting at the right. No 0, so I have to go down. I'm in from the top. Hit that, get close to my asymptote. Come in from the top, hit my 0, and get close to my asymptote. Bam. Sweet. Now, 2 extra things we need to consider here would be holes and multiplicity. What happens if I have the same factor in the top and the bottom? Now, you know, if I'm factoring numbers, if I had to have like 3 times 4 over 5 times 4, I could cancel those 4s and say that's 3 over 5, right? So I can kind of do that. I just can't divide by 0. Whether you're trying to cancel them, 0 divided by 0 does not cancel out. If you divide by 0, like all bets are off. The world explodes, okay? So whenever you're dividing by 0, it's bad. I can't divide by 0. So I can cancel these out as long as x does not equal 3. When x equals 3, nothing's going to happen. I'm going to get 0 over 0 and like, that's craziness. You'll learn about that in calculus. So I cancel those out for now. I get an end behavior of 1. I've got a 0 of positive 1, a vertical asymptote of negative 2. Okay. And I just remember here that when x equals 3, crazy things are going to happen. But barring those crazy things, I'm just going to like hop over x equals 3. I'm going to graph my function here. And what I do here at x equals 3 is that where that graph would have been, it's not on the x-axis, but where that graph would have been, I draw a hole to indicate that for all intents and purposes, those x minus 3s cancel out. But if x equals 3, I do not get a value. X equals 3 is not in the domain of this function. Here's another one. I feel like we don't have to graph another easy one like that. Here's a good one. All right, I'm going to have a hole at x equals -1. It's a good thing to find those like before you even start. Same number of factors on the top and bottom means y equals 1 is going to be my end behavior. Zeros will be at +2 and -3. Vertical asymptotes are at +1 and -2. Ooh, this is going to be a fun one. We haven't seen any like this that turn around in the middle yet. And at x equals -1, crazy things happen. So I'm just going to start graphing. 0 down. In the top. Now, there's no 0 here, so I've got to turn around and come back up. And remembering that at x equals -1, crazy things happen. Out the top, in the bottom. I approach my horizontal asymptote. I've got a hole there at -1. Resist the temptation to try and sketch that hole on there before you've sketched what your curve is going to look like. If you want to, you can actually cross those out and plug in -1 to find the y value of your hole. So just plugging in 1 for all those x's, I'm going to get -3 times 2, which is -6, over -2 times 1, 2. So that's a y value of 3. That's actually about where I sketched it, believe it or not. Fantastic. Very last thing here is to deal with the multiplicity of factors. So it's tempting to think that there are more factors on the denominator of this function than there are on the numerator, but there aren't because of that squared. That squared means that I've got x minus 3 times x minus 3. Right? I basically have like a double 0, or we could say this is a 0 of multiplicity 2. I'm going to go ahead and put my horizontal asymptote in there at 1, same number of factors on the top and the bottom, no coefficients. I've got a 0, I have 1 0 at +3. It's a 0 of even multiplicity, but it's 1 0. I've got a vertical asymptote at 1. I've got a vertical asymptote at -2. And if I start sketching here, I'm going to do this wrong first. Okay. Ah! I can't get up to this horizontal asymptote because there's no 0 here. So I know that I did something wrong. And let's examine what happens at this 3. If I plug in a number like 4, 4 minus 3 is 1, 4 plus 2 is 6, 4 minus 1 is 3, I get a positive answer. If I plug in 2, 2 minus 3 is -1, but -1 squared is +1. 2 plus 2 is 4, 2 minus 1 is 1. I also get a positive number. Because of this square, the sign of my y values does not change to the right and to the left of 3. I will bounce. When you have a 0 of even multiplicity, your function bounces off of the x-axis. And this allows me to sketch a graph that will meet all of the other criteria. We're going to see that in vertical asymptote land and call it a day. So same deal, but now we've got our things backwards. I've got a vertical asymptote at 3, a vertical asymptote of even multiplicity, remembering that I'm just not going to change sign there. And I have zeros at +1 and -2. Right, so sketching my graph. Close, close, not changing sign. So I will come in from the top, 0, 0, asymptote. Snazzy, huh? That's it for this video. I hope you found this helpful. Leave some questions in the comments if you have continued questions about how to graph rational functions. I know it can be a very scary topic for a lot of people, but trust me, you can do it. I promise. You got this.